machining. So that's going to be our topic for today. And I should have just started the recording. It'll probably tell me that fairly soon. Okay, so I'm going to share my screen and we'll see how this goes. So we are going to be looking at machining, and we'll kind of talk about some of the different definitions for machining, and we also will talk about some what might be considered alternative processes. I did want to just kind of point out that lab this week will be in S130, so that's the Harley lab. It's possible that when you plug in your computers, the screens will also work. It was my understanding that IT was trying to swap out some of the existing computers, and that should work. My expectation is that we'll be there like starting at 8 o'clock. And we all should be somewhat comfortable with using SolidCast. And so this week, you've got the assignment. We're going to start working on making a decision on what part or parts that we want to cast. And if we want to design a part, work on that, and then also the mold itself. If you want to work in groups, which I actually think group work is very helpful for this, you might want to have your groups kind of figured out prior to lab. So anyway, that's what we're kind of looking at this week. That assignment, I believe, is out on Canvas. Okay, so let's kind of like go into machining and going into, some examples. But before we really kind of talk about examples, I think we need to kind of define some words. And one of the things that can often be, rather interesting with machining as a topic is that depending on the audience or who you're talking about, it can mean two different things. In some worlds, machining is only a chip formation process. And that's where we classically talk about machining, where you have tools and lathes and drills and machining centers and milling and that type of thing. We will start with the chip formation process, but in other ways, machining means material removal processes. And so that could be chip formation, which sometimes we refer to as mechanical machining, although that is one that you might not have a lot of traction out in on the factory floors. We could also refer to machining as some of our abrasive processes. That's going to be more like your grinding, your polishing. We'll talk about honing and lapping. Sometimes that's considered an alternative to machining. Sometimes it's called machining. And then there's also some of what we call our non-traditional processes where we're using chemical or thermal or electrical. So that could be like laser beam machining, or sometimes we refer to that as cutting. That also could be electro discharge machining and so forth. So I think that I am going to use the word machining in the broader sense. And so if I refer to machining as, then I'm really referring to the broader, and when we talk about specifically chip formation. So most of when we look at machining in terms of the advantages and the disadvantages, we're referring to this more as a material removal process. But then again, when we talk about specifically chip formation, which the majority of machining is that classic chip formation. So let's kind of look at the reasons for material removal processes, and notice that I do say that rather than machining. And we're going to kind of go through the list, And one is going to be improved dimensional accuracy. When we look at our processes, you know, for casting or forging or powder metallurgy, you know, we can typically get the best accuracy with material removal. So we're looking at better accuracy than casting, deformation, and so forth. We can also produce features not possible with other processes. And we'll call those shaping processes. So, sharp corners. If you remember, when we're talking about design for casting, for deformation, for forging, for extrusion, rounded corners usually comes up. So if we need sharp corners, machining or material removal is great. Oftentimes we refer to this as a finishing operation. So for instance, to correct for changes in heat treating, for example. One area that we really haven't discussed in, well, it might have been mentioned in 321 or 322, is that the dimensional changes that we get when we do a heat treating. If you have a part and you heat it up, you're going to have thermal expansion, and that thermal expansion is maybe uniform on the heating, but certainly on the cooling, it's not going to be. And so because you have this uneven heating and more importantly, uneven cooling, you will get dimensional changes. And a lot of times that shows up as distortion, and it also can show up as residual stresses. So residual stresses and distortion are sort of different sides of the same concern or issue, which is uneven cooling, and therefore you have uneven thermal contraction. And so anytime you heat treat a part, your dimensions are not going to, you're going to lose some dimensional accuracy, both in terms of the actual dimension and then also in terms of the shape. So if you have a part that you need to have like high dimensional accuracy, oftentimes you do need to do a machining operation afterwards, after a heat treating to fix it up. So I have a couple more. There are some special surface characteristics. One could be a pattern, and this we would refer to as the surface lay. And then certainly our surface finish, really we're talking about roughness. When we look at our kind of our list of surface roughness and process, we're going to see that the machining processes, there are machining processes that are going to give us that smoothest surface. Now, when we talk about a pattern, there's good and bad news with that. There are some machining processes that leave a pattern, and that's not always a positive. But there's also some machining processes that create a pattern itself, and sometimes we want that. And then it also can be cost effective for small batches. So oftentimes we want to eliminate machining, but we also recognize that if you're not making a large number of parts, machining may be the most cost-effective method. Okay, so whenever we talk about what's the best process for an application, quantity is always going to be a factor in there. Okay, so now we have some limitations to other metalworking processes. And certainly one is we create waste material. That is going to be the material removed. So we remove a fair amount of material and the cutting fluid. So while we can recycle the material that's removed, it's going to have more oxide because the surfaces are going to oxidize. It's also going to be mixed with the cutting fluid, and so it's not going to be as clean as our starting material. And then we often use more energy and time. So machining can take longer to do the entire part. I also have that it takes more time, and it can create adverse effects on surface integrity. So the process of machining can actually change the surface of the material. Okay, so now again, this is not the greatest kind of slide going on here. What we find is as we're moving this way, we're seeing that R sub A is decreasing. And so down here on the bottom, we have our sand casting, which has the, like on the higher side, we do see that, you know, die casting and investment casting certainly give us smaller surfaces. If we look at some of these processes that are, you know, on the really smoother side, we'll talk about these. These are predominantly abrasive processes. If we look at some of our just standard processes, drilling, milling, you know, we're sort of seeing that they do tend to be smoother than our other processes, you know, our primary shaping processes. So again, this particular diagram just kind of gives us like the overall range that we might be able to expect from a given process. Okay, so let's start considering chip formation. And so when we look at machining, and we did have some in our reading assignment, and the book actually kind of does a nice job at this, we are removing material from the surface by producing chips. And so we need to understand what is this chip formation. So when we look at material removal, we are generally going to be kind of, again, removing some material. Sometimes we refer to the width of the material that's being removed as the kerf. Now, chips are removed by shearing. And so we know that shearing is deformation and fracture. And so when we machine and we produce a chip, we're actually plastically deforming the surface. So we can get some work hardening going on there. Now, every time I've ever kind of been involved in a situation where machining or chip formation, people love talking about the orthogonal cutting model. We're not really going to look in detail at that because that can take considerable time. But I think we should recognize that the orthogonal model of cutting is a two-dimensional, very simplified description of cutting. And there are equations and models that come from that, and that we also should have a little bit of an idea of what those variables are. It is an idealized process, and again, it's used to model the chip formation process. So prior to coming to MSOE, I worked for GE Super Abrasives, and I was more involved in the diamond and the cubic boron nitride producing business, but a lot of our customers were in the machining business, and we needed to make sure that we could educate our customers So the orthogonal model was one that was discussed. And again, we saw this. We looked at in our reading assignment what some of those angles are. And really, I really think we need to kind of recognize that if we hear relief, rake, or contour angle, we kind of know, oh, that's somehow related to the cutting tool in a machining operation. When you look at descriptions of cutting tools, you often do see a rake angle, and that is just one of those parameters we might see. So I think we know, again, just to kind of recognize some of the variables. We have the depth of cut, so that's going to be the amount, the thickness of material that's going to be removed. We have, again, kind of want to look at some of these variables. We have the cutting speed, and we'll notice that that is a capital V, and it's in meters per second. Sometimes we call this CFM, which would be cubic feet per minute. I think I'm going to erase that, because actually right now I shouldn't write this unless if I'm not aware of that. But we do have the cutting speed, which is related to the tool versus what we call the workpiece. So we call the piece that's being machined the workpiece, and then we do have these three angles: the rake angle, the contour angle, and the relief angle. So again, just kind of be aware of that. So we recognize, and we kind of, again, it's talked about in our book, that we realize, again, I want us to realize that the geometry of the tool is an important variable. It will be different for different workpiece materials. So that relief angle is one that, you know, this relief angle down here, which is somewhat related to how much plastic deformation is likely to occur, is smaller for steel and largest for plastic. So that means that the tools that we use for one material may not be optimal for another material. So what we're saying is the geometry of the tool may change with workpiece materials. Okay, and then the rake angle, which again is one that we often see when we start looking at specifications for tools, will depend on the tool material, the workpiece material, and then some other variables. We also kind of need to recognize, if you've done any machining, if we were sitting in class, I probably would ask for everybody who has been involved in a chip formation or a machining process to raise your hand. Most of you who have been involved in machining know that the temperature at the surface will get hot. And so one of the things that we're interested in is, where does the material get hot and what happens to that heat? So we want to kind of recognize that the material is likely to get hot right in front of the tool. And what we hope for is that most of that thermal energy gets taken away with the chip. When metal gets hot, we can have unintended heat treating, and we would prefer that not to happen. So again, we just want to kind of note that there are different forces in machining, but also we tend to see the highest temperature is just in front of the tool. And there's some other terms that we'll kind of see again. You do see this term springback, which we did talk about in terms of the recovery of elastic deformation, but that's not really going to be a big thing in machining. So we are interested, again, in the heating zone, because one of the things that I think is important to recognize is, how does the process interact with the material and the part, and what are those variables and how do they, again, influence everything? So we have a lot of friction, and we do generate a fair amount of heat or thermal energy, and then that can raise the temperature. Now, most of the time, we are going to use lubricants and cutting fluids or coolants can help. So some of the more common ones are going to be oils. We also have a fair amount of other liquids. There are environmentally friendly coolants and lubricants that tend to be used more now. In some cases, they recirculate. But anyways, we'll talk about some of the factors that go into the choice of a lubricant. But certainly, lubricants can help reduce friction. Coolants can help minimize the heat buildup, help with heat transfer. We also can see that sometimes the coolants can help mitigate the negative effects of a higher temperature. Okay. We want the location, and so if we kind of look at the location, we do see some of this heating zone is on the chip and some is on the workpiece. We do also need to kind of think about the properties of the material itself. If we have a material with a high thermal conductivity, that can actually help move that thermal energy away from the tip of the tool and workpiece. So thermal conductivity of the workpiece can help move the heat away. Oh, that's kind of interesting, you might say. So what does this mean for a plastic? Well, actually, when we machine plastics, it's kind of interesting. I mean, I find it interesting that because plastics are predominantly thermal insulators, there are some challenges with machining plastics and the increase in temperature, because in a metal, we see there's such high thermal conductivity, and that what we tend to see is that thermal energy is generated and it tends to disperse throughout the metal. With a plastic, that doesn't happen. So oftentimes it's concentrated, and that actually can influence both the quality of the surface you're producing, also the effect of the increased temperature on the tool itself. Okay. And then we also want to start considering sort of the power. We may talk about the forces that are involved in machining, but if we look at a particular machine, oftentimes machines are related by power, and we will talk about how do we get or calculate or determine the needed power. Okay. I think that variables are always fun. And I thought about, oh, should I write these down or should we talk about these? So I thought I'd just leave them here in the list and we can kind of chat about them as we go. So we want to look at our independent variables and then the dependent variables. So the independent variables are that which we can control. However, we're typically more interested in the dependent variables. When we talk about, oh, I want to notice that I don't have accuracy on this list, I don't have surface, because we can't directly control. I can't go to the machine and dial in a surface that I want. But what we can control, and what we often look for relationships between the independent and the dependent. So we can control the tool material and condition. And so we will look at, well, what are good tools? Well, we'll think about hardness, we'll think about thermal conductivity, we will think about toughness, We also will think about wear and a little bit on chemical reactivity. Certainly the tool shape, finish, and sharpness. Well, we know that those angles can be important. The sharpness of the tool is somewhat related to the geometry, but we know that tools can start, we go from a sharp point to more of a dull, and then the finish as well. Now the workpiece material, so the condition and the temperature. So in 322 we talked about spheroidizing, which is a very long heat treatment, but a spheroidized high carbon steel is much easier to machine than a quench and tempered. So when we talk about condition, we're really here oftentimes looking at heat treatment. And then the temperature, that is somewhat related to our, it would be unusual to heat a material just to machine it, but we can control to some extent the temperature. Now the cutting conditions, this is going to be things like, we'll talk about speed, feed, depth of cut, among other things. And we will look also at the difference between the cutting conditions from the machine versus the tool. And so for this one, we do have, kind of come down here, machine versus tool. And both of those are considered independent variables. We just do have to calculate them differently. We might choose one and then calculate the others, but these certainly are, and we will talk more about this as we look at doing some calculations. Certainly the type of cutting fluids, the characteristics of the machine tool, and then the work holding and fixturing devices. And our book kind of talks about that a little bit in terms of our dimensional accuracy and in terms of how supported is the machine, or the work piece. So these are things that we can control. Now our dependent variables often are what we're interested in. So the type of chip produced. Again, we don't have time to go into this, but there are different kinds of chips. If you have done any machining yourself, you're aware that you can sort of have what we call a continuous chip, where the material that's removed just it's one long, they tend to be spiral. We can have some chips that almost seem like they're very fragmented. And the type of chip can be related to the quality of the part we're producing. The force and energy dissipated in the cutting process. That is something that we can model, but we cannot directly control it. The temperature rise in the workpiece, chip, and tool. So again, what we'd prefer is the chip take most of the thermal energy. We'd prefer the tool to get the least, because that does affect tool life. And then the workpiece is sort of in the middle. The wear and how does the tool fail? Here we have, again, the tolerance and the surface finish. This is often what we're very interested in, but we can't directly control it. Oh yeah, here we go. Okay, so we sometimes refer to the chip formation processes. Some books make a huge deal out of there are 7, and here they are in terms of, and here we even see the 7 basic machining processes. And, you know, we've got turning, milling, drilling. Here we go, drilling. And then there's a few others as well. We're going to look at, in our book, kind of discusses turning, milling, and drilling. And we also will kind of look at speed, feed, and depth of cut. So I will look at, well, actually, let's kind of look at these in a little bit of I want to say detailed, but when we talk about the processes, one of the things that we're interested in, what rotates and what moves. Because when we think about like speed, feed, depth of cut, so speed is generally going to be what is rotating. Feed is generally going to be what is moving. So if I look at a turning operation, so in turning, the workpiece rotates and the tool moves into the rotating workpiece. Okay. In milling, we have, so in milling, the cutter or tool rotates, and we have relative motion of the cutter to the workpiece. So sometimes the work moves into the cutter, sometimes the cutter moves into the workpiece. But again, in milling, it is the cutter that rotates. And then in drilling, we see that the tool rotates and moves into the workpiece. Okay, now, I think most of us have probably seen a machining operation, but I am going to see if I can test my, okay, what's happening here? I thought I would, here we go. Ooh, oh, I want to keep those. Okay, I want to see if I can, let's see if I can go ahead and share, and maybe we'll watch a couple real short, what? Oh. Okay. Huh. This isn't going to, I don't think this is going to, let me see how this is. Screen 2. No. 2. Headset. Huh. I'm not sure why it's being a pain. Let me try this one. Huh. Okay. I'll have to figure this out. I'm not sure why it's not working. because I wanted to sort of show you some quick videos on a machining operation. So it could be that for some reason it's not happy with my with having the what do you call it, the my device going. Like, so it's kind of telling me that if I want to have the computer sound, I can't use my microphone. So I don't know, but let's look at some of the important things. On Thursday, probably on Thursday, we will start doing some calculations for some different situations in turning and milling. We're really not going to do a lot with drilling. So again, when we talk about variables and we talk about some of the equations, especially that material removal process, we want to always kind of have an idea of, again, how do the variables influence the final operations? What influences surface finish? What influences tool wear? What influences power? So when it comes to speed, again, when we're talking about turning, our speed is the workpiece or part rotation. And so that's going to be in, again, revolutions per minute. And then in milling, this is going to be the tool rotation. Okay. So again, we're going to look at again, variables, and we will see the equation that kind of helps us with tool life, and that is very related to speed. And so in milling, it is the tool speed, and in turning, it's the workpiece. Speed, on the other hand, in turning, is the tool moving along the workpiece part. And again, this is generally going to be in feet per minute, where speed is likely to be a rotational. And then the milling is, again, the movement of the tool into the workpiece, or the movement of the workpiece into the tool. In our machine in the basement, we have the feed in the case down in our machine. We call that the table feed. The cutter stays stationary. The cutter can move up and down, and it does move up and down, but the table moves into the cutter, and so that would be our feed. Okay. So now, if we start to also kind of go through some of those variables, some of those independent variables, we can kind of talk about this. Now, as we read about, and we have in our reading assignment, we sometimes have free machining alloys. And so we can't, now from a property standpoint, I'm never really super excited about adding sulfur or lead to materials. It doesn't necessarily have a good influence on the mechanical properties or on the ability to heat treat. But if we want to help machining, then if we add lead or sulfur, and as our textbook says, that can help with chip formation, maybe a little lubricant, and in many cases, especially with a sulfur, it is related to forming those inclusions. So we do have free machining alloys. We do have to be kind of careful with these, but these do machine better, so less power, less temperature, better surface than we would see a non-free machining. Also, just sort of some general kind of concepts, materials that have a high hardness or a lot of hard particles decrease tool life. And that just kind of makes sense. And then in an interesting way, we also have to be careful with chemical interactions between the tool material and the workpiece. One that can be kind of surprising until we kind of think about it. If we think about it, diamond is carbon and steel is iron with ME323, iron carbide. And so what we see is that if we machine, especially if we have high temperatures, if we machine if we machine steel with diamond, you can actually form an iron carbide layer on the diamond, and then you're essentially cutting with iron carbide, not the hardness of the diamond. So we do, and that's just one. There are some other ones that are involved as well. This is the one that's probably the easiest for us to understand. So again, sometimes we have to look for a cutter that not only has the geometry for a particular workpiece material, we also may need to look at the material composition as well. Okay. Now, machinability, this is one of those properties that is kind of a comparative or a relative property. We may say a material has a particular value of machinability, but it oftentimes is going to be related to like a core material. But a material that has good machinability is going to easily give us a good surface finish and surface integrity. So it's going to be a material that is not likely to be easily damaged. It's going to be a material that allows a long tool life, that has low force and power, and that has an easy collection of chips. So it's one where the chips form nicely. They don't get too long. They're not too short. So, but it again is a relative property, and it's not a theoretical property. It's one that we get by experimentation. But it is one that we may see on MatWeb or like in handbooks. Now, a material property is specific energy. So MRR, this is material removal rate, and that is going to be dependent on the feeds, depths of cut, width of cut. So, you know, and this is going to be in cubic inches per minute, for instance, and then your specific energy, this is a material property, and it is going to be power divided by material removal rate. So here we have the specific energy of some materials. And again, it's horsepower divided by cubic inches per minute. So that's why you have the horsepower minutes per cubic inch. So one of the things that we might see is like how high steel is. So, you know, and if we compare that to aluminum or magnesium. And so what that means is that, you know, steel is about 2.5 times that of brass. So if we had a certain, you know, if we were machining a particular material under certain conditions and it was brass, and we changed to steel and didn't adjust anything, it would take like about 2.5 to 3 times more power in order to do the steel. So and again, our systems, our machines are often related by power. Okay. So we'll kind of just probably finish off fairly soon here. We can kind of talk about materials in machining. Again, let's talk about the cutting tool itself. We talked about the workpiece. Oftentimes, though, we might choose a material by its machinability, but oftentimes we choose a material for its mechanical properties. But our cutting tools, we want high hardness. Now, hot hardness, this is the hardness at our machining temperatures. And so we do see that some materials have a high hardness at room temperature, but at a higher temperature, their hardness goes down. So hot hardness is a specific property that's looking at what is the hardness at a high temperature. We also need toughness. Sometimes these two properties kind of go opposite. Toughness is going to help us with impact resistance. We also need wear resistance, which would be, again, where is the removal of material when we have contact, and then chemical stability. So I think that this is a good place for us, I think, to stop, and we can start here on Thursday, and we also will be looking at some calculations, and we can kind of, again, continue our discussion. So I don't always like to go right up until the very end, and I may attempt to figure out why